frameworks. We could do a full training session of 2 hours on each of them. So there's a lot of training material online if you're interested, and I have links through the talk. So the first thing I wanted to look at was TensorFlow. It's open source machine learning library, originally started off out of Google Brain team. Right, like the way it's set up now, there's a high level Keras API, and Keras used to be a separate thing by itself. Now it's kind of pulled into TensorFlow. So it gives you an API in Python. Like I said, for the general thing, they're modular building blocks, so you can create and train models. You can assemble a bunch of layers, and the common use cases are supported out of the box. But then there's flexibility, like if you want to write a custom block or can create a new layer or different loss functions you want to set up, you could do those sort of things. And starting with version 2, they've kind of made eager execution the default, so that makes you that lets you develop things piece by piece instead of having to wait for the entire graph to be set up and run optimally. So this is nice for someone who's used to Python kind of development environment to just use it. And there are lots of pre-made estimators for training, evaluation, prediction, and you can export all of these. So if you want details on how exactly to use things, and Paul will walk you through some examples today, but there's a detailed guide online, and there are tutorials that are pretty nice, walk you through right from the basics. So Pytorch is another such platform where again, it's got a hybrid front end, so you could actually run in eager mode and then switch over to the graph mode for speed and optimization. Again, has quite a deep integration with Python, lots of pre-trained model repositories. The nice thing with Pytorch is there's a huge ecosystem of tools that's been already built on top of that, so you could go and look at that too. And there's a quick 60-minute kind of tutorial for beginners that I have linked there. So those are kind of the most commonly used tools. So how do you run those on a system like Expanse or previously on Comet? So we've had primarily two main approaches. One is to have Singularity containers with everything included in them, which you will see, and we publish the definition files for these container images. So in case you want to add something to them, you can always do so. But our containers typically have most of the packages that you need. And we also bundle in GPU drivers, or at least with CUDA, we can actually pull it in with the --NV flag. But we have all the setup that's needed, so the container is straightforward and easy to use. So today's examples will essentially use the Singularity approach. The other thing you can do is do a conda or mini conda based install in your own directory. This obviously gives you more flexibility on what you can install and add things as you want pretty easily. The thing to be careful if you go down this route is the driver on the system can only support one level of CUDA. For example, the driver we have right now can only go up to I think 1102 on CUDA. So, and if you just blindly install a conda-based install that pulls in the latest version, that may not be compatible with the driver that we have. So, if you're going to do conda or mini conda-based installs, check the CUDA version it's pulling in, and then make sure that it's supported on the driver that we have. So that would be the one thing to be careful about, because a lot of recipes will just pull in the latest versions of everything, which is fine if the driver is the latest. But for us to change the driver takes a while, because there's a lot of software packages that are built based on the current drivers, and every time we upgrade, we have to check every one of those packages. So it's not something we would do like very quickly. And then the reason I bring this up is because in a cloud kind of environment, it's very common to say, oh yeah, just upgrade the driver, right? Because you're just following recipes. That's not going to be that easy on our end. So just be careful about the versions you're installing. So most of our tools, like the machine learning and deep learning tools on Expanse and on Comet, basically are being enabled through Singularity. One of the reasons we did this is because these packages are constantly upgraded, and the dependency list is really not that easy to keep updated in a standard environment. So what we typically do is put everything in the Singularity image. Now we could also do things like put all the dependencies in the image and then let you build the source application from source within that Singularity environment, and that's also possible. So in terms of run options, most of these are run on single GPU nodes. That's what we've seen, and with 4 V100 GPUs, a single node has quite a bit of processing power. And we have 384 gigs of RAM on each node, so we're reasonably good on the memory aspect also. And a lot of times people use them via Jupyter notebooks. There are multi-node options, but it's quite difficult to set up via Singularity, and right now we haven't really set that up, but it's in the pipeline that we'll get Horovod going, so we could do some of these things. So couple of example run scripts, and these are in CM shared examples SDSC. So if you're going to look for examples, that's the place to go. And this is not just for the machine learning and deep learning applications. This is true of most of the applications that we install. We try to start putting examples there. Obviously, you can't do it for every package, but all the common ones should be there. So what we have here is, and if you've run on Expanse, and I'm sure all of you have since this is week 10 now, it looks like a pretty standard Slurm script. You have the job name, the account, so remember to change that account to your own allocation. And then you have the partition, you have the nodes, and task per node is 10. We have 40 cores on each node, so 10 cores is basically 1/4 of that, and we're kind of saying, okay, we'll take the fair share of cores with the GPU that we are requesting. So you're requesting 1 GPU, and the memory is about 90 gigs, and yeah, this just leaves enough buffer so that 4 jobs can fit on one node. And then it's just loading the Singularity module. And if you look down here, it just runs Singularity exec. And if on Singularity, there is an option to bind in external directories. So we're basically doing /scratch will show up at /expanse within the container mount. And then the --nv pulls in the drivers for GPUs. And then we just use the Singularity image, and then followed by the actual command we want to run. So like the Python 3 and this example. Now, one thing to keep in mind is this exec line is only for the command that you have in this line. So it's not like you can follow this up with some other command without the Singularity wrapper. Then it's going to end up running in the regular environment. So if you say have a bunch of scripts that you need to run, the best thing to do is put it in a bigger script, and then like a master script, and then run that through Singularity. Then that should make it pretty easy to run at that point. Similar thing for Pytorch. Everything is the same except for the image that's changing bottom of the. So instead of the TensorFlow image, I have the Pytorch image. And this particular Pytorch example, basically it's an MNIST handwriting detection, digit detection example, which is kind of the standard. It's like the hello world of deep learning. And this example is actually within the container, so you can just call it directly. So if you want to run this through a Jupyter notebook, there's a slightly different approach. So one thing you can do is, I have this Jupyter notebook example in the shared examples SDSC. So you can copy that over to the TensorFlow directory, and then in your home directory, and then launching the notebook. So Mary, have they looked at Galileo already, or this is the first thing that they're seeing of it?
This would be the first introduction to Galileo, but I
Okay.
think we talked about Start Notebook
Okay.
before.
So for now, I think the thing to remember is that this is a nice uh, wrapper script and packaging that we have done, where it will launch the notebook, and I have some snapshots on what shows up, and I'll also walk through with an interactive session in a bit. So what we are doing is launching a notebook using the allocation, the use 300 that needs to change to yours, and then so I have both a CPU and a GPU example. So if you're going to look at Paul's example that needs a GPU later on, use the second one here. And so the dash P is the partition. So I'm looking for the shared partition, and I'm asking for 16 cores and 32 gigs of memory, the dash M there, and a time of 30 minutes. And you can ask for more if, like, say, for example, in Paul's examples, if you want to keep the node alive for like 2 hours, just ask for 2 hours there. And the format is hours, minutes, and seconds. So 00 hours, 30 minutes, and 0 seconds. So that's basically a 30-minute job. And then we are just telling it that we need the Singularity Pro module loaded, and basically using the Singularity image. So this image, if you notice, is the same one that I had in the previous example script.
Just a comment. I put a note into the chat. We have a training user guide on running notebooks on Expanse
Okay.
and Comet. It's called Notebooks 101. It uses a different client called Start Jupyter, but we're replacing it with Galileo. They do the same thing.
Yeah.
And if there's time when Paul is done, we can do a live demo.
So Mary, I'll just walk through it now, actually.
Okay.
Like, I'll just walk through one of these.
Okay.
So then it's pointing to the working directory. So remember, I copied all the files into the TensorFlow directory. So I just made that the working directory in my home directory. And when you do that, you will get something like this. It'll tell you all the launch parameters, and then it'll give you the job ID. So for example, it says your Slurm job ID is this 2 million something out here. And then the most important thing is at the bottom of the output, you have this HTTPS address, which is a one-time thing associated with this particular job, and there's a token. So number one, don't share this with somebody. It's unique to each job, and while the job is running, that essentially gives access to your notebook, and access to your notebook is essentially access to your account. So you need to be really careful with, don't put it in any public place, and don't basically give it to someone unless you're okay with them looking at your files and looking at your account. So, but what this does under the covers is launches the notebook, and then goes through a reverse proxy server and connects back, so that you have a HTTPS connection to the notebook. So normally, if you run the Jupyter notebooks, there's no that security level is not there. So potentially somebody could be snooping on your traffic that's going by. So this kind of works around that. And then all you do is take that and stick the link in the browser, and you will basically be running on the compute node that's running that job, but you will be accessing everything through the browser. And this lab mnist example is, I think, what Paul's going to use. So that example, you can double click on that, and it'll pop up this window, and then That's the notebook that's running using the GPU and or the CPU, depending on which script you try, which option you used, and you can just walk through it. So let me stop here and actually do this so that you can kind of see all the steps. So I will share in the meantime. Okay. And these slides are online, so if you don't have to follow along right now, you can do that at your own pace. Let me see. So I should share this one. So I'm just going to share the terminal. So and move the terminal over so that, oops, that didn't work. Yeah. So everyone can see the terminal?
Yes, and the font is big. Thank you.
I can make it a little bit bigger. Okay. Yeah. So all
That's
I'm
good.
doing is using the same command. And by the way, if you, that's my home directory. Let me just go here. So if you look at that, there is the MNIST Python notebook. Okay. So I'm going to I'll do this using the regular compute node. So I'm going to do the command that I had there. So as you can see, it basically it's got my account info. The partition is shared. It's 16 tasks per node. It's asking for 32 gigabytes. So basically you're getting 2 gigabytes per core. Time limit of 30. The notebook directory is the TensorFlow directory, and this is the image that we are using, the TensorFlow image, so version 2.3. And you can see this HTTPS address here that's out there. So I'm going to stop sharing this and open a browser window and paste that. So you will see, okay, this happened very quickly, but if the job is pending, you will see the status as pending. But so now already the job's running, it's connected to the notebook, so I just,
Mahi, you're not sharing anymore?
oh, okay, sorry. Let me just, yeah, okay. Now you see it okay, right?
Yes.
Okay. So basically it popped up that notebook and I can just step through this. So you can see it's import from TensorFlow, it's importing Keras. So I can do a shift enter, and Paul's going to walk through this example, so I'm not going to go too much into detail. But you can see that it's loading the training set here, and those files are in the examples directory that I had in the slides. So, and then just go on stepping through and setting up the model and, you know, all the model layers, and Paul's going to explain these like a convolution and a max pooling and all those things here, and basically assemble everything and start running right with the model. So you can see it's running now, and this will be running on the node that I got from the scheduler, or if it's a GPU node, it's going to run on the GPU node the scheduler gives us. So it's quite straightforward once you are in this environment. Like, and this is nice because you could, you know, change things here and rerun and do all your development in an interactive way. So that's the nice part about going through a notebook kind of approach. And once you're, you know, happy with some model and everything, you can always export this Python as a Python file and then run it using the script that I had before, without having to go through all this interactive stuff. So let me stop that. Now, one thing to remember, and I'll share screen on the terminal again, which is this one. One thing to remember is cancel the job once you're done, so that there's not, that you're not wasting any time if you're not running, and B, you close out this connection that's active. That's basically a look into your account. So I'm going to cancel that and just make sure the job is gone. So scancel and the job ID, and the job's gone. So I can safely assume that no one can connect into that again. Because once you stop the job, the scripts or epilogue scripts on the system will kill all the tasks that are associated with that job. So let me now go back to the presentation. Let's see. Oh, that's interesting. Where did it go? Oh, it's here. Okay. All right, back to the presentation. So we saw how the browser came up, and I mean the browser link becomes active, and you can use that. So the last thing I want to talk about is Horovod, which is the distributed training framework for TensorFlow, Pytorch, and MXNet. So what we saw before was basically running on a single node. And like I said, you could use all the resources on that node, like say 128 cores if it was a CPU node, or just use all 4 GPUs and 40 cores on the GPU node. So you could do that. But now if your problem becomes too big for one node, or you want to speed up things and use more nodes, you have to have a distributed framework. Now TensorFlow does have another option of doing distributed TensorFlow with parameter servers, and that can be tricky to set up, especially if you're going through the Singularity environment, because it involves remote SSH based setup. And the problem with SSH is when you do a remote SSH, it's going to end up in the regular environment. So the Singularity environment gets lost when you do that SSH. So there's some tweaking to be done to do that. So it's a lot easier to go the Horovod route, which basically leverages MPI, and it just uses MPI to do the job launch. And if you wrap all your MPI binaries uh, with the Singularity image, then everything has the right environment and it picks it up. So that's the route we'll go, and this is available on Comet, but we haven't set this up for Expanse yet. So uh, uh, I don't anticipate any of the work that you're doing right now with these examples will need anything like this. But remember that this is an option. And the nice thing with Horovod is there is code additions, but it's pretty intuitive and doesn't need a huge change. So there's typically like an initialization, there is some assignment of GPUs, and then you can set the number of workers. And then essentially, and I'll show you that script, the Keras mnest script below. What really changes is the optimizer you use gets changed to the Horovod distributed optimizer. And then and there's a bit of work with broadcasting data, and then that's the end of it. Then you can just use MPI, and underlying you can use all the MPI implementations of all reduce and all gather for the gradient computations. The nice thing is for the end user, they don't have to think about, oh, how do I write that piece and all those things, because that's all been done and kind of uh, wrapped into this distributed optimizer from Horovod. And so there is a example here, a nest example that I can, again, let me share that in the browser. And I'm going to go back and share this one so you can see. Yeah, this might be a little difficult to read, I think, but let's hope not too bad. Yeah. So this is like a classic, again, the hello world of deep learning, essentially the MNIST example. But so you'll see you're importing TensorFlow just like normal, and then you have this horovod.tensorflow.keras, and then you do an initialization. Here's the GPU stuff. You can basically do one GPU per process, per MPI process. And all this looks pretty much the same as before, right? All the convolution, like all your model setup and everything. And then you go out here, you have a little bit of adjustment for the learning rate depending on the GPUs. And then the main thing is your optimization is now a distributed optimizer. And then everything else is kind of very similar to what you have before. So it's a minor amount of changes, and they also do a check on the rank. Rank means which task number it is. So task 0 does a little bit of the writing and reading of the files and those sort of things. And that's pretty much it. So it kind of makes it a lot easier to use parallel computing across multiple nodes for some of these deep learning frameworks. Now, if you had done that on a parameter server, you would have had to set up the server separately and kind of distribute the work and do a lot of things by hand. So this makes things a lot easier. So those are kind of that's the quickest, let me go back to the presentation. That's the uh, very quick intro to all the tools that are kind of available and how you can run them on Expanse. There's basically all of these frameworks available. We are using Singularity, and you saw the high-level APIs that are basically available through Python usage, so you can easily incorporate them into Jupyter notebooks and kind of do an interactive development of your models and your tests. So at this point, I will stop and hand it over to Paul, I think. I'll maybe take a few questions if anyone has, and then hand it over to Paul. And like I said, you don't have to test this right away. You can do things like asynchronously or like follow along when Paul is doing his demo. Looks like we are good. Paul, you can take over.
Aaron, hopefully you can see my screen
Yeah,
now.
everything looks fine.
Yeah, we can see it.
We can see it. It looks good. Thank you,
So-
Mahi.
So as Mahi said, I'm going to do an introduction. I'm going to do a little bit of a general introduction to neural networks, and specifically convolution networks. Talk about the deep learning ideas and deep learning concepts and the parameters that make up these convolution networks. And then we'll do an MNIST tutorial. I'll talk a little bit more about other things that we see in deep learning. So this is partly just a general introduction to the concepts, and less of an introduction specifically to how things run on Expanse. But we can do the tutorial on Expanse. And so I'm assuming that everyone has some exposure to machine learning in general. I know you guys are coming from a variety of backgrounds. Well, hopefully this kind of relates to things you've seen before. Compared to, let's say, I've seen deep learning. When we talk about deep learning, there's really sort of three things that I think of for deep learning. Really learning complicated interactions about it. Some ways that maybe we couldn't necessarily identify ahead of time.
Paul, a quick thing. I think some people are having trouble hearing you.
Uh-oh.
Maybe bump up the volume, mic volume a little.
Okay, hopefully this is a little bit better.
Yeah, I can hear you okay now.
Should I talk louder?
Yeah, maybe a little bit. That should be okay.
Okay.
Yeah.
Okay, so deep learning, it's learning really, to me, it's like learning complicated interactions, compared to a regression framework. You think when you want to do nonlinearity, you would like introduce certain terms. Here we're thinking that it's so complicated, we have to let the network have lots of possible interactions. So part of it is, discovering complex nonlinear interactions, or feature transformations, or really in practice, when people talk about deep learning, it seems to be that we're talking about neural networks with many layers. So just to remind you, in general, when we talk about modeling and machine learning, we're fitting parameters, we got some data, and we got some function, and we're trying to fit things. So just to sort of find a wedge into this topic, if you think about what a linear regression model is, it's a function and parameters, and there's some estimation procedure, and there's something we're optimizing. With neural networks in general, what we say is, let's instead of choosing a linear model, we're going to make a nonlinear model, and using the logistic function, for example. So this was the standard multi-layer perceptron started out with the logistic function, and that's a nonlinear model. And the function looks something like this. It's bounded between 0 and 1 as a function of x, so it's a little bit sigmoidal shape. And if we just set this up in terms of a graphical network, we just describe it as a graphical network. Instead of writing down the function, I can write it down as a node with, let's see if you can see my pen. So I can write it down as a node, and there's some hidden, we call this like an input node, for example, and there's some input values, there's a bias term, which is the intercept term, and an output. So anytime you think about a neural network and you see someone draw a bunch of little nodes like this with a bunch of layers, really every little circle you see is basically a little function. So logistic function, of course, is doing a transformation of the input into the output. We call this an activation function. That's the typical terminology. And the nice thing about this is it's very easy to show that as you vary parameters, you vary the way this logistic function is going to work, the kind of transformation you get. So if you increase your weight, you're increasing the slope, and that's almost making it like a step function. If you take a logistic function, so here's a couple of logistic functions that just have different parameters. They can be very smooth, very sharp, very smooth. You can shift it around to the left or to the right, depending on the bias term. So just those two parameters, just a simple function, all kinds of instantiations, all kinds of different transformations, all kinds of ways of introducing particular nonlinearity, really. You can do, if you have layers, then you can add this together. So for example, here's two functions that are logistic functions with different parameters, and they're a little bit shifted. So here's my 0 point. If I ask you, let's say I have another layer. I'm going to add these together. Right? So if I add these together, what's going to be the output of adding these two functions? So if you just do a straight add, it's going to look like
I'm sorry,
this.
can I interrupt for just a moment?
Sure.
There is some noise when you speak, and somebody was thinking maybe your speakers are actually still on, which means that your voice might be coming out of your speakers.
Okay, hang on.
So if your speaker volume is up at all, maybe turn it completely down. But honestly, it's not something I've ever heard before, so I'm not sure what it would be.
Okay, how about this?
Well, turn it off. Make sure it's all the way down.
All the way down.
Yeah. Okay, give that a try.
Okay. So maybe this is better?
Well, I'm not sure. I think I'm still hearing it a little bit, but
usually I have to tell you, usually I use I have a external camera and a microphone, but we have 3 Zoom meetings going on right now, and I'm like the low person on the totem pole, so I don't get to use it because we only have 2 cameras.
No problem. Just you're doing fine. So sorry for that.
That's just the nature of our times.
That's right. So yeah, sorry.
Sometimes I get an internet unstable connection when we have too many Zoom meetings going on, but hopefully I don't get that today. Okay, so hopefully that's a little bit better. So the point of this is that, gee, we have all kinds of nonlinear instantiations of this logistic function, all kinds of different ways of transforming. You can add them together, and when you add them together, you can get even more complicated looking functions. So this is, you know, the logistic function, 2 logistic functions added gives you basically what looks like a cosine or a sine curve, and you know, this is a bump function. So and if you know anything from real analysis, bump functions like sines and cosines, combinations of sines and cosines can approximate any function. And so neural networks really are like that. You can approximate functions, any function in principle, which is not to say that you can learn any function. That's a different question. And so here's some other combinations, and I'm showing you on the left side, just, you know, you can play with this, you can enter parameters, and you get all kinds of different transformations of your input. So the point is, multiple layer networks can represent any logical or real valued functions. In that sense, they're kind of unbiased, but there's a lot of potential to overfit. So in general, we can add many layers. We can add nodes. You can have lots of input nodes. You can have more than one output node. And we can put it together with, you know, we typically draw out these lines. We draw this out as a network. And each line here is, you know, from output from one node feeds in as input to the next node. And there's some parameter associated, which we call the weight parameter. And for our multi-layer perceptron, the standard description is to say there's an input layer, a hidden layer, and an output layer. And the input layer has, let's say, P input units. The output layer could have K output units, depending on your problem. And we talk about the middle layer as being hidden units. And again, all these units have a bias, which we typically don't show. And again, there's a weight parameter for each connection. So as we build these networks, we're really, again, every little node is just a simple logistic function or logistic regression. But when you combine them all, it becomes a big system with a lot of parameters and a lot of possible nonlinearity that it can learn. And we have this idea of propagation. Excuse me, I would just put my hand on this. So when we talk about propagation, there's a forward and a backward propagation in neural networks. So forward propagation means we have some input values, and we're multiplying it by input weights, and an input weight, and first from the input to the first hidden layer, that's going to contribute, that's going to get propagated forward and contribute to output values at all the other nodes at the next layer, depending on the connection. So propagation is this idea that, you know, our input and those particular parameters are spreading out through the network. We call that forward propagation. And the back propagation is when we say, look, there's going to be some output and we're going to be able to calculate error. So only at the output layer do we have some signal. We can look at the error. And if you know from, from standard machine learning practices, we can take derivatives, we can find our gradients, use our gradients to update our parameters. And that's our big optimization step. And in this case, our optimization becomes complicated because we have to backprop those error signals all the way back to parameters in the first layer. So that's backpropagation is based on derivatives, and it's based on the chain rule of derivatives. So you take the signal that you got from the output, and that is impacting the derivatives for the layers before and the layers before that. And essentially, it's extending the chain rule, and you're passing back in error information. Okay, so that's the idea of backpropagation. There's a lot more one could say about that, and that's really a big challenge with neural networks in general. What's an efficient way to train a neural network where you have signals only at the output level, but you have lots and lots of parameters. So that becomes that becomes the main thing that drives how we implement neural networks and how, why we're using GPUs, for example. Okay. So just a quick overview of the algorithm, we got a forward propagation, a back propagation, we update weights, and then we stop training. So that's a training step. And we stop training when our validation error reaches some minimum, or we get some kind of convergence. So we'll talk about that, what that means in detail. All right, so that's neural networks. I have this little slide here of all the different kinds of functions you could use in these neural networks. I'm not going to go through these specifically, but the nice thing about neural networks is as you change the functions that you use for output or functions that you use for a loss function, and you change, maybe you can change the activations, you have a lot of variation in what a neural network can be doing, or how they're appropriate for what kind of problem.
Paul, there's a question
All
in
right,
the
so this
chat.
is my little cheat sheet that I think is, when we get later to look at the MNIST problem, there's certain parameters you have to tell it, and basically you're pulling off this kind of information. Okay, so our summary, multi-layer perceptron neural networks in general, they're flexible, powerful learners, and the hidden layers are basically doing a nonlinear transformation of our input. And that's the name of the game, though. The bad thing is on the flip side, lots of parameters, hard to interpret, and it needs more data. Okay, let's talk about convolution networks. And so for convolution network, I want to introduce this problem, the MNIST problem. Oops. Trying to move my Zoom thing. And we want to think about, these kinds of problems. There's a bunch of digits, and we're going to feed it to a neural network. And we want to think about, well, what are the features that make this possible? Even if you weren't doing a neural network and you wanted to, let's say, build a machine learning model, you would ask yourself, well, how do I encode this? What is the nature of this input? If you're going to classify digits, you might think, oh, a 0 has a hole in the middle. Okay, so what does a hole in the middle mean? And how is that different from the hole in the 6 or the 9? So these are the kind of things people used to do before convolution networks became more, let's say, more standard and more able to be computed. So let's look at this example. Here's the number 7. So I've coded I've given you the bitmap of the 7, and on the right side, I just set up, this bitmap over here. And I don't know if you can see this, but I just put in some value from 1 to 10. So this is not exactly a translation of the bitmap on a grayscale, but I just wanted to just give you a sense of, okay, there's a input, which is a bunch of pixel values, there's a bunch of zeros, and where there's features, we have some positive values. And what people, the way we think about this is that, okay, there's a bunch of pixels, and we're going to look at little patches. And we're going to look at little patches and ask ourselves, what are the features in this patch? What can we do to identify whether or not there's something interesting here? And you might think, well, actually I could look to see if there's how many positive values there are, or how big these values are, what's the maximum value. And what people have done for a long time is use filters. And this is an example of a filter where I have -1s on the left, +1s on the right, 0 in the middle. So anything that matches this filter is going to give me a relatively high output value when I multiply. So I'm going to do an element-wise multiplication of my little input window and my filter. And we can think of these filters as being made up of some parameters. And if you multiply it element-wise directly, I end up with a +3 in this example. Okay, so that's my image window, my little sub-window, times my, let's call this filter capital W, because it's a weight matrix, essentially. So if I apply this filter, I get a 3, and I could slide the filter over. I could apply the same filter again, and this time, the second time, I get a 7. And then I'm going to get I keep sliding, I get a 3. And if I keep doing this all over this whole little window I'm showing you, I can slide my filter over this patch, which is 5 by 6, and I end up with a 3 by 5 feature map. So I've translated this little patch into a map that tells me, okay, something about how the little windows, how every little 3 by 3 window relates to my filter. Basically, you're asking is, does it match up with my filter? So what are the highest values in this feature map represent? The highest value I have here is 21. In fact, all these values are pretty high. And that corresponds to this part of the number 7. So there's some, so there's some, we would call this an edge detector or corner detector of some kind. And that's the idea of these detectors. This is how people built computer vision model for it. And then if we want to, we could say, well, let's do a maximization step. Let's transform, we're going to do a little bit of a dimension reduction. We're going to take a 2 by 2 box and just tell me what the max is. So I'm going to do another filtering just to get the maximum. And this is basically, I get to take my 5 by 6 patch and transform it into a 2 by 3 feature map of edge gradients. All right, so that's really it's kind of a straightforward operation. And the tricky part of this is coming up with a good filter. So in computer vision, really, there's many kinds of edge detectors, many ways to scale them. There's a lot of techniques that people have sort of developed, but building features is hard. So if you have enough data, you would like to be able to learn them. And this is where convolution networks. So in a convolution network, the filters are weight parameters, and these are going to be learned. And in this context, we call this feature discovery. And in convolution networks, we decide, people have this figured out, sort of by trial and error, that a really good activation function to use is a rectified linear unit. The rectified linear unit looks like this on the lower right. And it has a linear part and a part that's 0. And the nice thing about it has some advantages over logistic function, which is it's not scaled, so that's kind of bad. And so sometimes people will put a hard limit on it. But the derivative is easy to calculate. And the derivative doesn't, it's linear for this. If our activation is greater than 0, it's going to be linear. So if the input's greater than 0, the activation is linear. So our derivative is linear, and it's easy to calculate. It's fast, and it doesn't sort of get with a logistic function, your gradients get smaller and smaller as you get to the edges. So the only bad thing is you have to be careful around the 0 point. So a convolution layer is a set of feature maps where each map is derived from convolution of one filter with the input. And that convolution layer that we're going to use, and for most time, what most people use, is the rectified linear unit as your activation point. All right, so convolution, so that's the basic idea of convolution and what a convolution neural network layer is. So we can kind of like take a step back and get a bigger overview. So the properties of a convolution network, there's a lot more hyperparameters. And so we have to think about, well, what are we going to do when we specify? What are the choices we have to make? One of them is size of the filter. So in the example, I had a 3 by 3 little window that I was using as a filter. And that tends to be what people have found works very effective. So smaller is better because you can be more general. If you have a bigger filter, you might miss details. So smaller is better. And instead of having a big filter, it's better to have 2 layers of a small filter, for example. The number of pixels to slide over, I usually see people recommending 1 or 2 as usually fine. Again, the smaller you slide over, the more details you get. If you're sliding over too far, you might miss details. because remember your little 3x3 filter is really trying to detect something that's kind of in the middle or middle part of that filter, maybe the middle column, for example, the one we did before. So if you're sliding over too much, you might miss things. But the smaller your slide, the longer it takes to compute. So everything here is a trade-off with computation. The number of filters. So this is a hard one to choose because every time you tell a network to say, okay, give me, a filter, you're going to get a different feature map, and it's going to perform that whole convolution thing on the input for every filter. And you can really think of every filter as giving you some feature. So you have your original input, you give a filter, and you say, okay, I think I have, like with the numbers, I should have at least 10 features that distinguish numbers. If you have less than 10 features, you're probably not going to distinguish 10 digits. But the 6 and the 9 are very similar, so there's another different feature maybe you need. So maybe you need more than 10, maybe you need more like 20. So this is the kind of thinking you have to have, or you have to go through when you approach what are my parameters for the convolution network. So the number of filters really depends on the problem. And in general, people use max pooling. It helps things, it helps you lower the dimensions, and it makes things run faster without losing information. So those are the main hyperparameters you want to think about. And so let's look at an example. Here I have some picture of a car. It's an image that's 224 by 224 by 3. There's 3 channels for red, green, blue. And this is your typical input in a convolution network working with images. And your feature map, again, depends on the filter size and the slide parameter. So if I'm using a 5x3 filter, for example, I might repeat this for, let's say, a certain number of filters. So each filter is going to give me a new feature map for the next layer. Okay, so I have a bunch of convolution layers. And I add a layer of max pool to help, like I said, make things a little bit more efficient, downsampling. Okay, hang on. Hopefully this is better. All right, so we repeat this over and over.
So Paul, can you hear us?
I'm sorry?
Can you hear us okay now?
Yeah, I can hear you.
Okay, there was a few questions in the thing. Your volume was down to 0, so you probably didn't hear. Okay, I think way back there was a question about how do you avoid local minima when you're doing the gradient descent kind of minimization? I know there's a
local minima.
They do stochastic approaches and like random sampling, right? On the
yeah, you know what? You got to remember something. Let me go back to that was several slides ago when I was talking about gradient descent. So the thing about neural networks, there's a lot of local minima, and you can't find the global minimum. You won't find the global minimum. What you do find is that there's a lot of minimum that are pretty good, and because you have, depending on how you build the network, if it has enough parameters, you're going to find that all your minima are pretty good. I mean, in general, let me go back to this picture. So that's actually a deeper question than you might think. When you have a network like this, it's very possible to say, well, look, I could reorganize these things. I could flip it around and flip the weight values around, for example, and have the same solution. I could have the exact same output just by making symmetric flips. So there's really a lot of global minimum, or a lot of minimum that are very similar to global minimum. And you're not gonna, unless you're doing really long searching, you're probably not gonna find much improvement. The marginal improvement with, let's say, longer and longer training with smaller and smaller learning parameters, smaller and smaller updates, you know, a more fine searching is not necessarily going to improve very much. So you really want to use validation error. And that's what we'll talk about when we'll show that example when we do MNIST. You really want to use the idea that you train until your validation stops improving, so your validation test, I should say. So you're looking at generalization.
Paul, you have a couple of questions.
Okay.
Um,
So I go to is it on
Mahi,
chat?
did you have a question?
So Mary, that's fine. I had my hand up because I was trying to get his attention on the speaker volume. So we're good, I think.
Okay, then take your
Maybe,
hands down, Jeff and
yeah,
Mahi.
yeah.
Thank
Probably
you.
Jeff had it for the same reason. So we're
Okay.
good.
Okay,
Thanks.
thank you.
Yeah.
Yeah, it's not, I mean, the global minimum, you know, it's funny because if we think about neural networks and we're thinking about it in terms of doing statistical analysis, you know, if you're doing statistical analysis or Bayesian analysis, you're used to thinking about like a global optimum, some optimum, you know, some parameter, some setting, some finding of parameters that you can sort of say, okay, here's like some significance or here's some real difference. So with that, you know, you don't quite get that same thing with neural networks, especially when you start building with, you know, complicated neural networks. When you build smaller neural networks, you know, maybe you could have something like that. So it's not quite like logistic regression in that sense. Okay, is there there's another question? Nope.
No, it's okay.
Okay, so, all right, so we're building up from one little simple node to layers, to stacks of layers, to, you know, many convolution layers. And typically in a convolution network, you know, you need a lot of data. You need some heuristics to avoid overfitting. Typically, we have some layers, some top layers that are then just doing, they look like a multi-layer perceptron. So we have a bunch of convolution layers and then essentially a multi-layer perceptron at the top that takes your convolution layers, makes your two-dimensional feature maps into basically a one-dimensional vector, and then performs some classification. So this is the, you know, output right here. And they're going to be a class output. All right, so this is the standard thing that's been going on with convolution layers. That's been very successful in computer vision for the last, you know, since, I don't know, 6, 7 years now. They've kind of been dominating all the computer vision conferences. And just to get you, you know, just to remind you, there's some different terminology. Sometimes you'll see applications where they talk about the thickness of your convolution layers, or sometimes it's called the channels. So depending on your programming environment, you'll see parameters with slightly different names. So just sometimes you have to make a little bit of translation. Okay, and as I said, the last layer gets laid out as a vector. So in this VGG, this is the AlexNet, I believe. So this is a particular network that was implemented, one of the early ones that were very successful, and they had 256 feature maps that got translated into and each feature map was 13 by 13 at the top layer. So it downsampled 224 by 224 into 13 by 13. And finally, you have to translate this into a vector. And then perform it. And this was performing classification for 1,000 classes. So what do the convolution layers do? What do they look like? So here is the first convolution layer and the feature maps. And for the AlexNet that we were just looking at. And so these features, they look like, they're basically edge detectors. And they look like Gabor field. If you're familiar with the computer vision world, there's, you know, different names for these kinds of things, like little Gaussian functions. These are like features in different directions, maybe, you know, different shades of gray, being on or off. But then we also have features that are color-based. They're kind of blobbish. And then you have you know, it's hard to know, like some of these, they seem to be either edge detectors or color. Some of these might be a little bit of both. That one looks a little funny. So it's hard to know like what exactly these features represent. They are just simple in the first layer for sure. And as we go up the layers, so here's our image. Our features become, remember, our features start covering bigger parts of the input, and they start representing higher level features or more abstract features. So for example, with the car input, you feed it into, you know, your convolution layer. Your first layer is basically looking at highlighting certain parts of this car. And as you go up in layer, as you go this direction, these features become more abstract, and they're just sort of, you know, they're less about the spatial particular pixels and more about, let's say, combinations of pixels. And it's hard to say what those features exactly are. In this example, at our output layer, we get a prediction of car, followed by truck, airplane, ship, and horse. So those are the top 5 predictions. And so that's the basic story of a convolution network. You know, they work really well for object recognition. Obviously, they're kind of built that way. They have like a special architecture. Again, lower layers have less filters that represent simple features, and higher layers tend to have more filters that cover larger regions of space. All right, so if there's any questions on that, I'm gonna keep going. So this is the tutorial we're gonna do. It's like Mai said, it's a hello world. And before I do it, I have a couple more slides. So I want to go ahead and just present a few more slides just to talk about, you know, deep learning in general, other kind of convolution network things. As I said, this is sometimes called feature discovery. So when would you use now, if you're familiar with machine learning, if you've worked with computer vision applications, you know that support vector machines were working pretty well in a lot of situations. Often you would use an edge detector, and you would use a support vector machine to look at the edge detector result and give you some classification. And I find that with small data sets, if you have a reasonable feature, a support vector machine can work pretty well and maybe better than the convolution network. So what's a small data set? Again, that's hard to say. Okay. Are these filters designed based on needs to describe some features, say a filter for tires or windows? So in a convolution network, you're not designing features at all. In an edge detector with support vector machines, you're using simple features that detect edges, certain kinds of edges. And so if you're trying to learn to recognize, let's say, an object or a car versus a horse, you're hoping that the edge detectors are going to be able to be combined with the support vector machine to differentiate the two. And the important thing to remember is that in those computer vision applications, you're looking at an edge detector at different scales, and you're combining them at different scales. And that's what a support vector machine can do for you. Now, as I said, if you don't have that much data and you're trying to learn some classification that needs some complicated some features, sometimes that's a better way to go. So I was looking at a problem with handwriting. I found that if you have less than 1,000 images, your support vector machine is going to do better. And I had just like 20 words. There's people filling in forms. And it was very noisy data. And so my support vector machine did better up to 1,000 images. Between 1,000 and 5,000 images, they were kind of the same. And then after more than 3, 4, or 5,000 images, the convolution network had enough data to learn that problem better. So what counts as a hard feature or a small data set depends. But that was just my example. Okay, but so here's, I'm not going to go through this slide. This is the different kinds of tools that Mai talked about. One thing, you might, as you know, there's some of these tools are available on, big tech companies have APIs that you can tap into. So the Google Vision, there's a Google Vision application and they have an API. You can run this from a Python program, so you can like feed it an image and get some classifications. And it doesn't do too bad. Here's an example. I was looking at some old pictures for some project, and it actually get the idea that this is musicians in here. And this picture, it predicted soldier because this person is holding up a stick a certain way. So that's the kind of, and that's not unusual to get this kind of result with these tools. The thing about these tools is, you know, you can only run a certain number of images before it starts charging you. At least that's how it was a couple of years ago when I was doing that. Some references. The good reference is the book by what's his name? I have it. Shalette. So if you're going to start deep learning, this book, this author right here wrote a really good book. That's a book about Keras and deep learning. Okay, so just a couple of other things to mention. So the nice thing about the convolution network is that there's a lot of networks that are available that have been pre-trained. So some of these networks that came out of the conferences, you can go download them and use them. And we'll look at an example. And so that's the kind of thing that you might think, well, support vector machines, you know, maybe I want to build something else. I don't have much data, but you have, well, I'll say more about that in a second. There's also other kinds of tasks. So we're in this phase now where people are doing not just classification, but detecting where objects are, segmenting the objects in the image, looking at bodies and getting key points. So these are built on different architectures. There's also, you know, recurrent networks is another different topic, which I don't have any slides on, and that's just whole another talk. Okay, transfer learning. So transfer learning is useful to think about. If you have a large model that's already pre-trained, you can get the convolution layers from a pre-trained model and apply it to your problem. So this is a common thing to do. It's a nice way to take something that's already been trained with a bunch of filters. So if you have that kind of problem or that situation, maybe that's better than using a support vector machine, for example. So what is transfer learning? Here's an example where there's a network called, this is the VGG network, which is the visual group, like Oxford visual group something. And they have a couple different versions of a big network that they've pre-trained, and it's available in Keras. You can just load it from a URL. And the idea that you can take all the convolution layers as they were from training. You can take all these convolution layers and then just reuse them. And then take your problem, just take the top layers and train them on your classification problem. All right, so I have a question. Are these filters designed based on our need to describe some filters? Oh, okay, that was the question we had before. So with transfer learning, hopefully if you have a problem that's similar, it's like another object classification problem, but maybe just some different objects, you can take one of these pre-trained networks and use the same filters and just train the classification part of the network. And this saves you a lot of time. If it's a dissimilar problem, if you have like, you're doing something completely different than object recognition, maybe but you want to start with those filters, then maybe you could maybe just keep the lower layer and just train the upper layer, for example. So depending on your problem, this could be easy to work with or maybe a little bit tricky. So there's a lot of people have experimenting with different kinds of architectures. So here there's a convolution network, but a convolution network doesn't have to be one layer feeding the next. It could have different paths. You can combine, you can merge paths and split paths. Here's a network that has a different path just to give you output that are bounding boxes. Here's a network that it's a bunch of layers, but at the end, it's going to do a pixel-wise prediction. So it's going to give you segmenting, it's going to give you masks instead of just giving you a classification. And there's some different variations on this. How do you get a mask that tells you where the object is and gives you a different mask for different objects? So in this case, there's a cat and a dog, and they're masked as separate objects with different colors. Okay, so this is also another kind of special architecture. I mean, is it special? I don't know if I should call it special or just CNNs have this flexibility. You can build architectures, different architectures.
Paul,
So
there's
here's
a
the question.
Yeah. Oh,
If you have two trained models and the output of one produces input to the other, does the composed model need to be retrained? So you have two trained models, the output of one is input to the other. Depends on what the situation is. There are reasons that there are situations where people do things like this. And if you're trying to get one model to trick another model, you can have it feed that input and see if, you can have one model, say, producing images of a cat. Another model telling you, is this a cat? And you can have one model say, well, look, I'm going to produce a cat that's a little bit funky, and see if the other model gets it. And then the other model says, oh, is that a cat? Okay, I'm going to try to change the parameters. So you can do things like that to get models to sort of train themselves. I mean, this is what people do in what's sometimes called adversarial learning, or sometimes people do this when you're doing games, like teaching a network to learn a game. You have two models competing against. So you can, again, the point is that neural networks have this flexibility that you can combine them in different ways. All right, so Facebook has these models. They took over Cafe, and then they started building these models that are specifically like for people stuff. And they do object detection, they do a bounding box around people. So I was looking at these old images for a different project and trying out this Facebook thing. And so it's also a pre-trained model. You can download it, you can run it. I was running this on Comet, it was on Pytorch. It's a little bit, Cafe, I found Cafe doesn't have as good documentation as Keras, but it sort of works, has the same ideas. So this was, so it did pretty good with finding people. It didn't do very good finding the body of on the cross. The object segmentation network, again, it does pretty good. There's an object parts where it identifies key points, and it's been trained to give you, I don't know if you can see these lines, but there's a line here, a line here. So the body parts, a line for the arm and elbow. So it's been trained on body parts, and you can, this was again, these images are paintings. They're not quite like photographs, but it's actually getting a decent job at some of these images. It doesn't get, people, here's a person kneeling, wearing a big dress, so you can't see the legs at all. So it doesn't do perfect. It's not as good as a human on this kind of image, but it's getting there. Okay, let me, so these are pros and cons. I'm not going to go through that. I will go through this. This is cute. So this was an example of a test somebody did, and we'll do something like this as well. We can do something. So this is some pictures of animals that the human could classify, but the network didn't. And here's some examples of pictures that a human couldn't classify, but the network could. And this is a few years old now. I don't know. Maybe the networks have gotten better, but humans are probably the same. So it's interesting. It's not quite. It's interesting to think about, like, what are the differences here. Okay, so I'm going to go through this tutorial on the MNIST, and if you didn't get the data, or if you don't have the tutorial, and if you're on Comet, if you're on Expanse, I have what you need over here as well. So let me go ahead and flip my screen to Where is my tutorial? Here it is. Okay. So again, I have the same, I started a session and I have a tutorial running for the MNIST program. And this is the same one that Mahi was showing you. I'm just going to go through a little bit slower than you did. So I have, typical Python, I import a bunch of stuff. I'm importing the main thing in here. I'm importing Keras and particular Keras modules. So I'm just going to run that. I have a bunch of data. I'm loading data. These are images. I've taken these images and I've saved them as NumPy arrays. So I just did that out of a little bit of convenience. But the MNIST images are available on the web. And I'm just going to load them. And I'm just showing you the shape. So I have 5,000 images there. These are 28 by 28. When you run with the convolution network, you have to make sure they have the right shape. So in our case, or rather in the convolution network, you have 4-dimensional input. So each image is 3 dimensions. And the first dimension is going to be the number of images. So because these are binary, because these are black and white, I'm going to have to add a new dimension. That's what the new axis function is doing over here. And then I'm going to reshape them, make them float 32s. I'm going to normalize them. Okay, so that's my data preparation. I just taken images. I've got now my training set is 5,000 by 28 by 28 by 1. And I have 10 digits. So my training output is 5,000 by 10. I'm going to run this model sequential, which is basically telling Keras we're just going to run a standard a standard halfway of layers. It's going to be one layer feeding the next. And basically with Keras, there's the higher level API over TensorFlow. And if you want to run sequential or recurrent networks, those are the two kinds of models you could run. And I don't remember what other standard models they have. But if you want to do special things like special architectures, I believe you would go to TensorFlow. Okay, number of filters. I have 16 filters set here, and that's going to be, so I have this convolution layer command. So I'm going to add a layer, my first layer. So this is the first layer I'm adding to my model. It's a convolution layer, and that convolution layer takes a certain number of parameters. These are the parameters we mentioned in the slides. Number of filters, the size of the filter. I'm going to start with the stride, how I'm going to slide it over. That's also called stride. I'm telling it that the channels, remember when you have an input image, you have 3 channels, red, green, or blue. Later, when you have feature maps, there are different layers of input to another layer. The number of channels is the number of feature maps. Okay, I'm using a rectified linear unit with the input shape, so I'm just going to run this. You can, the layer objects, you can look at what is the output of that layer. That's it. Keras gives you some functions to help you do that. I'm going to add another convolution layer, a max pooling layer, and then a flatten command to turn it into a one-dimensional vector. Okay, and I can again look at the output of that shape, the output shape of those layers. I'm going to add classification layer. And then when it's all done, I'm going to run this compile. And I'm going to tell it, we're going to use a certain optimizer. The metric is going to be accuracy. So this kind of assembles the layers. I give it a loss function. So this is a standard loss function for classification. And here's a command that's nice. You can do the summary command, and it'll show you all your layers and how many parameters you got. So right now, this is 70,000 parameters. For the MNIST problem, I don't need nearly this much. That turns out that's actually a problem that can be solved with a lot smaller network. But for our purposes, I just want to show you this example. So I have 2 convolution layers and then a max layer, a flatten layer, I don't have a dropout layer in this example, but if you know what those are, typically people show you this is the dropout layer. That just basically adds a little bit of noise, so it helps build some robustness and avoid overfitting. Okay, and then I have, I'm going to use this early stopping function, and I'm going to train it. And I'm going to save the history of my training. So I'm running this, and it's giving me my loss for the training set, my accuracy for the training set, loss and accuracy on the validation set, and it's supposed to stop. I said you can run for 50 epochs, which is like 50 times through the data set, and after 14 it stops because it's not improving anymore. And you can look at this validation loss. So the validation loss, it went from 0.27, 0.26, 0.2639. So once the validation loss increases, that means my generalization isn't working as well. And that's the way you choose how to stop it. And so I'm not necessarily finding a global minimum, but I'm finding a spot where if I kept training, it's going to get worse and worse on generalization. And that's really what we're after, is having good generalization. Okay, so we can plot things. Oh, no, that's just the object that gets saved. You can look at, there's an evaluate function, so you can go and you can evaluate certain points. I can plot, oops, why is this not working?
Paul, I think I fixed this in the other one, but there's a, I think you have to import the PLT. You have it below a little bit. If you go down, yeah, those imports, those two import lines, you can grab those and. Yeah, it should be good now.
There we go.
Yeah.
Okay, so I'm just plotting the training and validation accuracy. Let's see, let's go down to what I really want to show is some of these images. So here's an image, which is the 5, the very first input. And I have, the nice thing about Keras is it gives us some tools to look at the layers and look at the weights. So remember, the weights are like the filters. So my layers has a method to get weights. And I can take those weights, sort of rearrange them, and show them in a mosaic. So this is going to be just plotting them. I'm just rearranging them and I'm just going to plot them. So remember, I had 16 filters. So I have 16 3x3 filters. And remember, when we were looking at the edge detection example, those were simple to interpret. But when you look at these filters, it's not obvious what they're looking at. What are, are they picking out an edge? Are they picking out a corner? It's just not obvious. It's just a combination of things. And that's really typical for problems. You can look at the weights and you're not really going to see what they're doing, what the feature is. However, for this problem, if you go back and change that filter size, so instead of 3x3, maybe we'll have time, we change it to 9x9 or 12x12. These filters will start looking more like something you could recognize with digits. The other thing I was going to show you is, okay, so we can gather also the outputs from each layer. So Keras has this way to get the output, to set up this function, which will, for each layer, I'm going to save the output. And then I'm going to run the actual model with some input. In this case, I'm only using one image as my input and the output. And then I'm going to save it. I'm going to manipulate it. I'm going to get the predictions, and I'm going to show some plots. Okay. So these are the shapes of my layers, my output layers. And now I'm going to output them as a mosaic, as another mosaic. All right. Again, the input image was a 5. And this is what the output looks like for the first layer, for the 16 filters. So if you look at this, you say, well, what are these filters doing? Here's a a filter that's basically only has 2 pixels that are active. It's almost like, I don't know if that's useful, to tell you the truth. Some of these filters, they seem like, okay, this one is kind of, it's looking, maybe it's highlighting certain parts of the 5. Some of these filters are they look very similar in terms of how bright these pixels are. Some of them looks like they are just highlighting certain parts of the 5. So it's very hard to interpret. But again, it's just the 16 filters apply to these things. Let's go up. Let me go up and rerun this since I think we got time. Oh, okay. Where's the, okay. So I'm going to change my first layer. Instead of a 3 by 3, I'm going to make it 12 by 12. And rerun everything. Okay, so it's I think more accurate than the last one. So now here's my 12 by 12 filters. And when you look at this, it's much more tempting to look at this and say, oh, you know what? This is like this one on the bottom left. It looks like it's, a filter for having part of an image that's like a little bit of a line in this section of the image, or this section of my 12 by 12 patch. So it's a certain kind of edge. And you might say the same thing for some of these. This one looks like it's actually a little bit of a curve. This one that's second row and third column. So as you get bigger filters, right, they're going to represent something that's more abstract and more related to the classification task. All right. Any questions on that? If you get a chance to play with this, that's the kind of thing you can play around with and test out. Let me show you guys one more thing. We're almost done, I think. Or at least I'm almost done. We talked about the transfer learning stuff, and that you can find the networks, you can load the networks that are pre-trained. So I have this, I was using this network for a project, and this is the VGG19. So it came out in 2019. It was the 2019 conference from the visual group in Oxford. I don't remember the GGs, what the other G stands for. And so I can load this. I saved this model already. I can run it. Oops, almost run it. Oh, you know what? Hang on. I am. I loaded the wrong one. Where is my? Here it is. Okay. So I was looking at the old version of the code, which was running on Comet. And Expanse, I had to change a few things. Okay, so I load this model and a summary, and this is a summary of this model. So this is the model that it works on 224 by 224 images. It's got blocks of convolution layers and then a max pool layer. Okay, so someone asked about the filter. Sorry, I'm like 10 seconds, 20 seconds behind when the questions show up. On what basis do you choose a filter? Is it a trial and error process? In general, if you're doing general object recognition, you want to choose a 3 by 3 filter. You want to keep it small. You want to for all your filters, you want to err on the side of small. You're going to find that smaller will give you more generic filters, but just probably run a little bit longer. you want to use small filters and have enough layers so that your higher layers can cover, enough space, right? Because your small filters are only 3x3 patches. As you go up in layers, a combination of those smaller filters will cover bigger patches. The two 3x3 patches from two different feature maps are going to cover like a 5x5 patch in the next layer. So that's I mean, you have to kind of have a figure out like what the nature of your problem is to come up with what kinds of filters you would want to choose, or what size filters you would want to choose, I should say. So this is the VGG network. So I loaded it. It's got a bunch of layers. It's got basically 5 blocks of convolution layers. Okay, hang on a second. I got another question. No. Okay. So this VGG has 140,000 parameters. I'm just going to run some images. So I got a bunch of cat and dog images. I'm just going to run it. I'm preparing those images. I'm going to just look at the shapes just to see what they are. I got some labels from the VGG network to see what actually the outputs represent. I'm just going to run these in. So this network was trained again for a 2019 conference, some 1,000 objects that were being tested. And a lot of those objects were dogs and cats. And this is always a good way to end the talk with pictures of animals, right? So this is a cat, and let's see what the network predicts. It predicts that it's a border collie with a score of 0.32. Okay, now that's not too bad, and it does predict that there's a carton in the image. So it didn't quite get it as a cat; it got it more like a border collie. Here is a picture of a cat, and it says with a 0.19 that it's an Egyptian cat, and the second and third guesses are also cats. So that seems to do pretty well. This one is also a cat mostly. This one, it looks like it's predicting with a strong prediction that it's a Schipperke, which I think is a dog. And so like for us, we can see that it's a cat, partly because for different reasons. So it's not obvious like what the network is picking up on in this case. Like maybe the particular examples that were given had pictures of a dog from a certain angle, for example. This is a cat. It does get it as a cat. This is also predicted to be a cat of some kind. Now this one is a little bit different. If you see this picture, now we're looking at cats, so you're already biased and primed to know that it's a cat. But if I show you this picture without having shown you any other, without any context, what do you think you would predict? Well, here's what the network gave. Arctic fox, some kind of lagopus. Oh, Arctic fox or white fox, a weasel, and then a cat or a gray fox. So looking at that picture, you think, oh yeah, you know what? It does kind of look like almost like a wild animal or something. All right, so there's another cat. Let's look at the dogs. Cat. Okay, so here's the dog. Okay, so we predicted a dog. Here's another kind of dog. It predicted a dog. That's a pretty clear dog. It predicted a Labrador. So I think, with really good pictures, it's getting even the kind of dog right. All right, that looks like a shepherd of some kind. It's predicting a dog, but the German shepherd is not the first prediction. Here's a dog standing up, and it still predicts a dog. So that's actually impressive. All right, so there's a dog. Another dog. Gets pretty good with that dog. All right, now what about, let me go to this last picture. All right, so what do you think it'll predict for this dog? So a couple things, it's a cartoon. As far as I know, this was not trained at all on a cartoon. So So that could throw it off a lot. So the first prediction it gets, but you know, obviously for a human, we see it as a dog. For a network that's been trained with real images, here's what it predicts. Table lamp. The second prediction is lampshade. If I show you this dog, you think, oh yeah, can you see the lampshade in there? Okay, so I think, yeah, you can sort of see that, oh yeah, the shape of this outline here, this edge, if you're just looking at edges, the shape of this head looks like a lampshade. All right, and but the nice thing is, you know, I loaded this network, and again, you can load this network. You can find examples of how to retrain this network if you have a different problem. When we do our tutorials in the summer, we do run this with a transfer learning tutorial where we train you take this kind of thing and we'll train a network on classifying dogs or cats. Okay. So that's all I have. That's my last slide. Hopefully I've given you a sense of, you know, the idea behind networks, or at least convolution networks. Hopefully I've given you a sense that, you know, the idea of deep learning is not just for images, it can be for other kinds of problems. So audio, you know, audio problems or speech recognition, for example. You know, it's a little bit different kinds of filtering, right? If it's something one-dimensional sequence in time. There are, you know, other kinds of architectures, other applications, you know, working with the masking. You can, you know, there's certain biomedical image applications you can do with a network that's producing segmented output. So that's the other take home, is that, you know, these networks, there's certain flexibility in a model where you could just, you know, generically build input and output and have it learn these transformations. All right. All right, so that's all I have. Again, if there's any questions, let me know. If you guys have questions later, you know, that's also fine. I can respond over email.
Thank you, Paul, and thank you, Mahi. If anybody has questions, feel free to unmute and ask away. I'll stop recording so you don't have to worry about that.